we're going to be talking about the energy zone, particularly, obviously, but also we'll start off talking about general systems and how they might go together. So the whole idea is we get a general idea of how all systems compare, well, as many as possible, and then to look at what should be in a proper heating system, and I'd value your opinions later, and also just talking about the structure of the system. It isn't talking about appliances, and it's not talking about type of pipe or anything like that, or open systems or sealed systems. It's just a general gist of circulation and delivering heat and whatever. So the idea that I would have is that by creating a proper system, the heat goes faster, it gets out there more efficiently, it takes less fuel, the customer's delighted, your reputation goes up, everybody wins. So we'll start off with the most basic system that everyone knows. It would be the S-plan, but this would be an open version. So we're going to take seconds and just look at each one, but I want to take particular note of something about this. When people put in a system like this, or they put in a sealed system that has, say, hot water and 2 heating zones, or they put in maybe a combi boiler that has 2 zones, there's never any consideration about this area here, the common area, let's say. And yet, if you look at bigger systems, and you look at what everyone who's involved in the component manufacturing or anything to do whatsoever with heat distribution, they say that you must adhere to strict rules for that area. So what I'm going to be doing is looking at bigger systems and then come back to it. So we're looking, so all of those systems, as far as I'm concerned, are the same. It doesn't matter if they're open or sealed. Water is leaving a heating appliance and traveling towards zones and splitting into directions, coming back and hopefully spreading uniformly or in the direction they should go and the amount they should go to the different areas. So the most common system that seems to have started the whole ball rolling with regard to zoning, it started really in America because close couple T's and the like of that came from companies like Caleffi and Taco and Taco and whatever. So where you have a close couple T's or a common center point, and then you have a flow header and you have a return header. So what they say is that if you, for example, have a 35 kilowatt boiler, and the pump is sized correctly, to move the water through that boiler and you're going a short distance, you need 28 millimeter pipe. But when you get to the header, the water in the header should have a velocity of at least, or not at least, but at maximum 0.6 of a meter or 2 feet a second. And then if it's a 35 kilowatt boiler, you need a 42 mil or 1.5 inch header. So if you, again, on the return, of course, that's going to be common. So what I'm going to do in a lot of situations with this is show one boiler, but in reality, the images will be showing 2 boilers, but really you can take 1 or 2, it doesn't matter. If you're annoyed with the second boiler, close one eye, it doesn't matter. So what I'm saying is the amount of heat, no matter where it comes from, through the pipework. So for a 35 kilowatt system, you should have 1.5 inches. But just suppose you had a bigger boiler, say 70 kilowatt boiler or 2 35 kilowatt boilers. You now need, yes, you can take 28 mil or 1 inch from each boiler, but now you need to go to 1.5 inches on the common header, and you need to go to 2 inch on the flow header and 2 inch on the return header. So if this system is broken into just say making up 70 kilowatts, just suppose we have 10 kilowatt load, no problem, 3/4 pipe, 22 mil. 30 kilowatt, you need to go up to 28 mil. Then you have a 14 kilowatt on load 3, and it's 28 mil again, and 16 kilowatts on load 4. So they total up to 70 kilowatts. So these pipe sizes we all understand, but there seems to be a kind of a misunderstanding of what's happening here. And a lot of people complain about having issues with their systems, that some of the zones are not heating as good as others, some are drawing in air. And a lot of the time, it's because the common header isn't big enough. What actually happens, the water trying to get from this point to say this zone, when this pump is drawing, this pump has to pull against the vacuum that's been created by this pump and this one and this one. So therefore the last pump or the second last pump or the combination of the two of them, if the pipework is too small, is now going to be causing air to be drawn in on the vents, and it's going to be causing hassle with them circulating. And remember, as the different loads start to change with TRVs closing down and people turning off rads, there's no one said it could be here. It could be that the vacuum might be caused because of water activity is very strange, as you well know. The vacuum or the lesser pressure might be between the second and third or first and second zone, whatever. But the way to guard against it, these are the general criteria. So you deaerate the system, you get the water pump pressuring from the neutral point, or the neutral point is created by the open vent or the expansion tank. So you're pulling water through the boiler, maximum pressure in front of the pump, pushing through the correct size header, and then you're pushing off out onto the zones with the particular pump load. With the close coupled T's, you probably know that the primary pumps, or the pump if you have one boiler, will be circulating through the close coupled T's and back to the boiler. And then the other pumps can draw from that, provided they haven't got an extraordinary resistance put in by the contractor who hasn't, let's say, got his common headers right. So we look at different systems and how they might work. Oh, one thing I want to say to you, do you see, to do this system so correctly, if you have a 70 kilowatt boiler, you'll need 10 2-inch T's and 2.5-inch T's. That's a lot of money. That's a lot of fittings, and it also a lot of joints. But if this is, I didn't make this up. This is the rules of the game. If you look at the people who write the books on the subject, and if you certainly look at the brilliant videos from the like of Califfy and Teiko and other companies like that, you'll actually find that this is absolute standard practice. So if there are now different types of systems, and just keep in mind, we don't have to mention what size the boiler is over here, but you have to take into account if it's just a heat pump with 6 kilowatt output or 20 kilowatt output, it doesn't matter. The pipe size here must be an extraordinary size to carry the load. Within reason, the biggest header you can have, the better the circulation, because now the pumps all have an equal chance of getting at the volume of water. In this situation, there's a very critical thing that I've never heard anyone discuss clearly, and it's to my mind, it's critical. And say, for instance, the boiler has a thermostat on the return. For the boiler, for the water to reach the return, it has two choices. One choice is that it can go through the header, up through a zone, back down, and back on the return. But if the returns can't get water because, for example, some of the zones are turned off and enough water can't get through the zones to come back around and turn off the boiler is delivering enough heat for all of the zones. So the only way it can turn off, how it does turn off, is the heat builds up in the boiler. It can't get out. And because it can't get out, it can't get at the return. If it can't get at the return, it can't satisfy the stat. So the boiler turns off based on inefficiency. It turns off because it has no reading of the system, because the only reading of the system it can get is if water comes through the zones and goes back. So these would be, say, motorized valves. And then, of course, if you do have motorized valves, people would sometimes put regulators. I know with commercial work, you would have to put a regulator on each one, so you know precisely how much water is traveling in zone 1, 2, 3, or 4. If you don't have regulators, now you're going to have to do your balancing on the rad valves, which of course is standard. But I'm talking about the correct theory. You should know how much water is passing in each circuit. But if you see, again, go back to what I was saying in the first place, you might have this set perfectly, and this set perfectly, and then you turn on this, and it's a huge zone, and it's going to take a lot of the volume. And so now you're back compromised again. So the effect of the fourth zone might affect the first and second, and vice versa. The first zone might affect the third and fourth. But that's where the balancing hassle comes in. You just think you have it right, and then you put on one more zone, and it all changes again. But the point I take away from this is the water has to get back to the boiler, and this system, even though it has an automatic bypass valve, the water has to fight past that bypass valve to get back to turn off the stat, or to give the boiler information that the system is up to temperature. So if you take it that then you could have, say, a common header, which means the water leaves the boiler, or two boilers, again, makes no difference. A particular return water goes through a particular boiler into the common header, and its only job is circulate around the common header. The boiler has nothing whatsoever to do with the zones. Then the zone takes the water at the correct rate through a non-return valve, so that you won't have any backfeeding. So when say the common boiler, if there's one boiler or two boilers or three boilers are on, their job is heat the header, and the zones then come back around. But again, we have the same scenario. The header must be able to deliver all the water across, and also the returns, or each zone must take the correct amount, because there's a golden rule. You can't take out more than you put in. So if you're putting in, let's say 50 kilowatts of heat or a certain amount of liters of water in the boilers, you can take out 60 out of the zone. So again, there's where the balancing comes in, and it's critical to know the flow rate through the boiler, in as much as that it's critical to know the common number, or the accumulated number from all of the different zones operating. The reason I showed this, and the only difference with this sketch and the other one, is that again I'm showing the T's, but remember, if this was a 70 kilowatt load, these would have to be 2-inch T's, and the bypass would have to be able to accommodate enough water for the water to flow around, so that you have no resistance. And again, it's just to show that again you have all of these T's that have to be put together in a proper way to make sure that your system is right. If you have the exact same system and you turn it facing upwards, like again in America, you have a lot of boilers and basements. But of course, if you're in a two-story house and you've got a circuit upstairs, you have to prevent the heat rising up. So you're going to use a check valve in front of it. But you also could have drifted heat from the return, just like a solid fuel boiler works. You have a gravity circuit that could potentially go up through one pipe circulation and feed backward into the radiators. And you get guys saying, my motorized valves have failed. And what actually is happening is, the hot water is passing underneath the return pipe looking upwards. It drifts up through the center of the pipe. The wall of the pipe cools the water, and the outer water falls back down, and you start to circuit within the pipe, a one pipe circuit, and then the heat reaches the radiator and it's off. The heat travels along the top of the pipe. Heat loses heat in the radiator, falls along the bottom of the pipe and down the edges of the pipe, and you've got a perfect circuit through one pipe. It's not something I created. One pipe circulation was actually deemed as a way of air conditioning even one time, and whatever. And certainly with gravity systems, you would take like that into account. Be very careful of drifted heat going up through the system. So in this scenario, they reckon that this is a very good way to do it, because you are, like if you're mixing, because when the pump is pumping on, it has a fully open bypass. So what it means is that the heat can get at from the boilers, can go through, say, a buffer. A lot of people say this is the best way to do it. I particularly don't. And there's reasons why I wouldn't go through that. But the buffer so heats to whatever, you're getting your coldest water from the bottom of the buffer. And then you put the heat in. When this pump takes it, there's no resistance, goes round the bypass and comes back in. So you've got a perfect open circuit the whole way. And then as each zone decides to turn on a pump, it can take its correct amount of mixing. So again, a very logical way to do it. But to my mind, the buffer is a huge amount of water to heat if there's no reason. And secondly, it's going to take up a lot of room, and buffers are not cheap in any case. So if you take this scenario as well, if you're taking close coupled T's from a primary loop off the boiler, so you have two boilers feed through a given circuit, let's say you have a 1-inch circuit, and you take your close coupled T's, the idea is that the close coupled T's should never be more than 4 times the diameter of pipe away from each other, because you're making this a common area. So the same pressure exists at this point as it does at this point. But now you're again in a situation where if this is drawing water across, this pipe must be big enough to take the load. And then if all the pumps are turned off, the boiler still has a return circuit that can actually satisfy the return stat, and the boiler turns off on efficiency. But remember again, the 0.6 of a meter per second, you should be passing through the headers, the flow and return headers. So in this scenario where people use low loss headers, everyone would reckon that it's the panacea of all heating problems, because it has deaeration, it catches dirt, you have a drain point at the end. But there is a few issues that I'd like to talk about on that again. But you do, of course, have the situation where you have an open bypass, the water can flow back to the boiler. So it's just another way of doing it, but you've given yourself a relief on the water circulation back here that can slow the water down, which is a great idea. And again, if the header is sized properly, you're going to find that even on a standard small system, the header is about the equivalent of 2.5-inch iron pipe. When I say standard, that would be up to, like, let's say 50 kilowatt, 70 kilowatt or something like that, maybe say 50 kilowatt. Anything more than that, the header has to go much, much larger. So if you're 100 kilowatt, your header might need to be a 4-inch diameter pipe. So as again, as the zones come on, the heat's going to drift up around, and then when it comes down to return, the return can backfeed up. So again, you need those non-return valves to deal with any potential back circulation. If you take your low-loss header and you have your heat loads, you can have one pump and then motorized valves. So yes, it works. Yes, it's common. But I'm saying to you, if you think about energy, there are reasons why this might not be the best, but sometimes people have to use it anyway. In America, they have a very interesting device. It would be where you'd have closed tees. This is a fitting you would buy, and inside there's like an injector. And the idea is that if you have zones, the water flows through here. It can't get through the injector in each tee fully. So some of it goes up around and comes back down, and it all carries on again. And the same applies with this one. Then when the water is passing in these bypasses, the pump can take it and heat the zone, or not take it, and it just carries on the same as before. So in that situation, that's fine. But again, you do have a lot of resistance on the pumps that you might not necessarily need. They even have a system, or they use that system, where they don't have zones, but they want to have, say, one pipe system. And you might say one pipe systems are a thing of the past, but think about this. If a heat pump or a condensing boiler needs a maximum temperature drop, you're trying to increase the delta T, the difference in temperature from the flow to the return, it actually is a very good idea to consider taking the heat, strip some energy away, go on to the next one, strip some energy away. So when you get back over here to the final one and you're heading back, you can actually calculate exactly what your temperature drop would be. So it's not such a bad idea to consider a one pipe system. I'm not saying people would be inclined to do it today, but it's not a bad idea at all. It's something well worth looking into. Now, people who use low-loss headers and who talk about systems in this configuration sing the praises of this system, because, forget the zones for a second, if this pump is on and these bypasses here, this one and this one, this one and this one, are regulated properly, you have a very definite circuit that passes through from the flow onto the return every time. And if the zone comes on, it pulls water from that bypass through the mixing valve, obviously, pulls it around and delivers the heat. The cold water is offered back into the return. So again, you've got a very, very good opportunity to have, you have a full bypass on the boiler, you have an air vent, you have a slower water volume. And so the pump will have very little work to do, because it's constantly got its rate set to do what it should be doing all the time. So it's, again, a very good system. But I draw your attention to the number of T's. On this circuit, 2, 3, 4, 5 T's, 4 circuits, 20 T's. Yes, it's a great system, but it costs a lot of money, and there's a lot of time put into get it balanced and right and whatever, and it's certainly a lot of labor. And I know, because I started my time in 1970, and I know what it's like when you've got lots of fiddly bits of pipe work to do and try to keep it neat and whatever, make sure you don't forget to tighten something, whatever. So ultimately, if you were to look at what might be a great system, if you had a low-loss header that had multiple connections and they didn't have to go through a big pipe, that they were all coming from the same place, you might say, so you've got a bypass, and now none of the T's affect any other T, so that would make sense, wouldn't sell, it wouldn't be a viable product. So certainly this spacecraft looking thing might be, in theory, be a very good idea, because again, there's no one zone is affecting another zone. You've got a completely open circuit. So all of that seems to make sense. And the people who like low-loss headers say that low-loss headers work all the time. And I'd say yes, but there's a lot of hassle trying to get away from the low-loss header with neat pipework so that you can get to the zones without crisscrossing everything and giving yourself a lot of hassle. But I want to talk about the low-loss header. When low-loss headers were first introduced, it was never to do with condensing boilers or heat pumps. It said that it was for back-end burnout, where the back end of the boiler, if it got cold water would condense onto the back of the boiler, and the boiler would actually form acidic fumes that would eat through the boiler. So the idea of the low-loss header was to give a constant circuit through the boiler to prevent back-end burnout. And then the whole idea was to mix the water. Nothing has changed except someone's now called boilers by a different name. And yes, there's a different function, condensing and heat pump. But now they're saying that the low loss header prevents mixing. It's impossible because metal boxes are metal boxes and heat is heat and flowing water is flowing water. So you will have mixing inside in this. In other words, some of the hot water that comes in here invariably will go back to the boiler because it's displaced by the cold water that's coming back up. So you've got a mixing of the temperatures that's diluting the flow going out to the system and heating the return going back to the boiler, even though the boiler relies on the coldest water and the zones rely on the hottest water. So I just don't agree with the fact that suddenly they've changed the definition of what low loss headers were initially designed to do to what they say they do now, when it's common sense, the water mixes. So of course, I'm coming around to the energy zone. Many people don't understand what's happening inside it. But if you could look at this in a very simplistic way, we'll talk about this little thing here separately. If water flows in, say here, and flows along, there's a pipe coming from the other side, but there's a baffle that prevents this water going through that pipe. So it flows outside it, and we'll talk about that again, and it travels along through a perfectly open pipe. The chamber in an energy zone, the smallest possible energy zone, is the equivalent of a 2.5-inch iron pipe. The middle chamber, for all of its what it seems to be able to do, is actually only an extension of the left-hand center pipe. It's where it's a round pipe here, and it becomes a square pipe here because it's just a way of conducting the water over to this critical point over here. If this is connected to the, I'm going to class it as the system's neutral point, everything is connected at this critical area. So the water coming in from a boiler here has a 2.5-inch pipe to get over to the perfectly open bypass and directly back to where it came from. If water comes in on this side, it hits the same baffle, but on the inside of the baffle, turns back on itself. And even though it's piped on the right-hand side, it flows from the left to the right in exactly the same path past all the open apertures for different zones, back around and down, and goes back to the boiler here. In fact, what some people don't know is you can take the flow in here and you could take the return over here. You could actually take the flow in here and take the return here. You can take a flow into any chamber into the top, and so even a flow could come in here. You could put, say, for example, a heat pump in here, just suppose, and you could put maybe an oil boiler in here, just suppose, but you're still reaching the chamber. So there's no definite rule. And the beauty of it is that it can suit your pipework. Instead of you having to bash an idea around your head trying to figure out how do you connect on, you're connecting to chambers. So how you connect to the chamber is completely opened up because each one of the flow connections arrives at the chamber. Each one of the return connections arrive at the chamber. I'm going to contradict myself in a while, but I'll show you there's a reason for it. There's another very important thing. When water flows in here or here, water will be tending to travel in a straight line. But to release air from water, you need two things. You need to break the water flow up so that the water becomes turbulent. And when it does, because it's the hottest water, the air will break away and rise to the top. And the distance from where the water comes in, whether it comes on this side or this side, is about 5 to 7 times the diameter of the pipe delivering across here. So in that distance, all of the air travels to the top and is scooped away. So people who would use energy zone regularly would say that the system becomes very quiet very, very quickly. Well, that's the reason why this baffle serves two functions. One is it prevents water from here going directly out and water from here going directly out, but it also plays a critical role in breaking up the water and causing deaeration. If you had an open system, this could be our expansion, but this is the most perfect place to put a cold feed because you remember the idea of the expansion and the cold feed should be in close proximity to each other. Well, they're 75 mil apart. So you could take an open expansion for a system from here, and you could take a cold feed into here. So again, each zone now, if you go back to the first diagrams, has a full access to the 2.5-inch header to take away whatever water, there's no conflict. And the 2.5 inches is made up excluding the volume of the pipe on the inside. So it means that it's extremely open for the water to reach. But another thing, the boiler pumps are assisting to push the water towards every open pipe. So instead of there being a conflict in the system, the water all flows in the same direction. So it works very, very smoothly if there's one boiler or two boilers. Same applies on the return. If the water comes out on its own and it loses heat, or comes out on, say, the second zone and loses heat, all of the coldest water in the system is now captured in the return chamber. So if you have a condensing boiler or a heat pump connected to the return chamber, as opposed to low loss headed where water can mix, you've got all of the cold water that can't possibly get at the hot water, even though it has an open connection. And that can be taken back either this direction or this direction, back to a heat pump or condensing boiler. And so you don't have the conflict. You now have a perfect open path the whole way around. So within reason, that's the general gist of the thing. So when I had showed you the diagram, I was referring precisely to what's going on inside. It's exactly what's in the diagram, but you can see this baffle that breaks the water up and prevents that water reaching over to that socket and prevents the water coming in here from reaching that. You see this shelf here is to stop that water so it won't go down the zone. And it causes part of the more turbulence here that causes the air to rise. There's a funneling area here that captures the bubbles traveling along, and there's a block that catches the air here, and you find that it releases the air in the system extremely quickly. Again, if a cold feed is brought in here, it's down into the system neutral point. And so if you had a condensing boiler, it could come down here. It does not mean that you couldn't put a condensing boiler here, because this is perfectly open to that chamber. So if you had a boiler, you could put the return here, and there's reasons why you would do that. We'll look at it in a while. So again, you can see the idea. The air coming in from either pipe drifts along and goes off out the return. And you can see here that if a flow comes in from here, it could travel along and go down. It could go out here, or it could travel along passing the zones and go out here. It could go out any one of those returns. If the boiler comes in from this side, it doesn't conflict with the other boiler. There's no need for any extraordinary devices. It just travels along, turns back on itself, and so again presents itself to each of the zones down through the neutral point, where every pump on this system, whether it's a boiler pump or a zone pump, is pulling water in from a pipe. Let's call this square area a pipe, and this is a pipe. That pipe has an opening here, and it has an opening here. This is the neutral point. This is where you would join your expansion and cold feed, or where you would join your pressure vessel. If your pressure vessel is joined either here, or here, or here, or you had a T here for your event and your pressure vessel up here, you're still at this area. And this is the critical area of every heating system, because you should know where it is. With an NRG zone, you can categorically point your finger and say, I know exactly where it is, it's here. So yes, I'm saying this is the flow chamber, and we refer to it as the flow chamber, and you can flow in from the left or the right, and you could feed back to a return from a boiler from here, because you are picking up the return, or here. But of course, if you this is the logical place, here or here, to take it back. But remember this, even though I've said that, you can watch the arrows, you can reverse everything. You could actually take the heat in at the bottom. If you had 3 boilers, say, you could take the heat in from boiler 1, say wall hung boiler, boiler 2, boiler 3, into the top chamber. You could have a pipe leaving and going to, say, hot water cylinder, and then you could have a pipe leaving here through a mixing valve, and now you've got a boiler collection manifold. It's the exact same device, but you can use it now for a completely different reason. So the direction is completely up to your own imagination when you're doing the design. One very critical thing is, by simply touching, you'd want to be careful not to have a solid fuel boiler full belt. But if you were sensing what's going on in the system, with your bare hands, you can actually touch the flow chamber, the bypass chamber, the return chamber. You can catch any zone. So if you have something wrong with a valve or a zone pump or whatever, by catching the zone pump's flow and return, you can actually see straight off that the water is flowing in a circuit better or not than another circuit. So straight off, within seconds, you're identifying there's something potentially wrong. So for fault finding, it's literally at your fingertips. So the point that I'm making is that this is the neutral point. The only places the flow and returns mix is in this area. They do not mix back at the critical areas where the boiler meets the zones. So it's taking the hottest possible water away. When it takes the hottest possible water away, it delivers the maximum amount of heat. When it brings the cold water back, that doesn't mix over here unless there's, like in the closed couple T's, a reason for it to go back that direction, because your zone pumps are too powerful, like you're taking out more than what you put in. So if you ever find that heat's drifting back up here, you know your boiler pump is too small. If your boiler pump is too small, you'll feel the heat drifting up here. If you have a thermal imaging camera, you'll see it immediately. In fact, there's a video online where one of these is being commissioned, and you can see it directly. The water's traveling the wrong direction and going up and feeding into the top chamber. So, but you can see now, people say it's just a low loss header. No, it's not. And it's just close couple of these. No, it's not. It's a lot different, because you're doing exactly, if you were to take a checkbox, what should you do? So then the checks are ticked in this area. So the dotted line, so is your system neutral point if your expansion vessel is connected to any connection directly connected to this one, or here. You obviously, if you're reversing the flow because you're using it as a boiler collector, you could actually put your pressure vessel, well, maybe not this one, but certainly over here. But any one of these are just perfect. So inside, in a thermal imaging situation, you can see if heat is coming in from a boiler. Just suppose you have a gas boiler or something, and you have 63 degrees coming in. In this situation, you can see that the cold is reaching back up to here. That's a giveaway there's something wrong with the flow pipe, because you've got cold water arriving back up here. So by changing it, by adjusting the boiler pump, you now have the flow rate right, and you can set your pumps just by fingertip. Of course, if you should have some kind of a thermal gauge to see what's going on. But in this scenario, you can see that this zone is calling, but this zone has just turned on, and that's caused too much water, so the heat's rising up. Now, where this zone is bringing back, now when it's adjusted, the hot water reaches right across to the last zone. The cold water is being pushed back down, and look at the differential. We've got from 65 to 39. And this system isn't up to temperature yet, but we've got about 26 degrees temperature differential. The pumps are taking the maximum temperature, and the returns are at the optimum temperature to cause a heat pump to work at its very best, or a condensing boiler to work at its very best. So basically, the story, sort of the idea, is matched by what you actually find on site. When we talk about NRG Zone 4, don't ask me why we did, but we classes, there's connections here, 1, 2, 3, 4. So you have four groups of connections here, the top being what you might use for your temperature sensor, or for venting, or for cold feed, or whatever. So this is an NG4 because it has two connections, two zones underneath. This is an NG5 with three zones underneath, and an NRG6 with 4 zones underneath. But just because, you remember, we can make manifolds to suit any job. So this was very, very useful, because the existing work had a flow and return coming across the boiler house ceiling. So we made a manifold to fit exactly onto it. So when the guy put it on the wall, his zones were able to go directly on, and he was able to take away his heat over here with the 2 flanges onto his main headers. He could collect the heat from here. He could collect the heat from 2 additional boilers here, 2 condensing oil boilers. I think they were 75 kilowatt each. And then he was able to take away 250 kilowatts over here. And again, this was ready for a heat pump for the future. So manifolds are not at all what they seem to be. You can make whatever size you want. So the idea is you go to the boiler house, you figure out the easiest way to pipe it, and instead of you trying to figure out how to make a certain thing fit, you make the thing fit what you're trying to do. Again, there's another job where there was actually a log burner on one side, and there was 2 condensing boilers on the other side, and 10 zones. Just works out very, very neatly. And then we do make panels as well. So if you are doing a job, you can make whatever size manifold you want with temperature gauge sensors put in wherever you need them. So for the building management system, we have a flow temperature, we have a return temperature, and we even have a bypass temperature, because there was multiple heat inputs into this device. And then we make the control to suit the job. So instead of the job dictating what you want to do, you can control what you want to do, and it gets rid of all of the hassles of confining yourself to bits and pieces of the normal way to go about it. And again, I don't know if you know, but we would make boiler house modules. So here there were 4 115 kilowatt boilers on the wall, with some 4-inch pipe behind, traveling on the back, connecting onto the manifold. And then there was 7, I think, zones. That's in a supermarket, on the roof of a supermarket. It was everything was prepared to connect onto the pipes, no matter what direction they came. So it was made a very, very simple changeover. The job was installed completely with prefab done in 3 days on site, less than 3 days. On the third day, it was turned on. So again, when I look at 2 boilers, I'm just saying you could take it on the left, you could take it on the right, but you can see if a boiler is delivering here, you can take your zones away, like heat load 1, 2, 3, 4, vice versa. You can take it on the other side, or you can have 2 boilers. When you use 2 boilers, you happen to have 2 spare connections. So there's no reason why you couldn't put a 5th zone and even a 6th zone. So now you have 2 boilers and 6 zone of a manifold that costs about 300 quid. No tease, no messing about. You screw the box onto the wall and your boiler house is designed with multiple zones. There's one other thing I want to say. This is a pump on a 1-inch pipe. If it's a pump with a flow and return on a 1-inch pipe, there is absolutely no reason why this couldn't be a header with 3 motorized valves, or say with 3 other pumps leaving it. So you could actually have 3 zones here and 2 zones here and 4 zones here, because if 2 1-inch pipes will do a house, there is utterly no reason why you couldn't have multiple zones of those pairs of connections. But of course, back to the rule again, you can't take out more than what you put in. So if all your zones add up to a certain amount of water activity, you must introduce that water in from the boilers. If it doesn't, the zones can't work. Again, here we're back where it's just upside down. So remember, you do have to protect against heat rising on the returns, but that will work away absolutely perfectly. So you could put a manifold at a ceiling, say if you're in a basement boiler area, connect up onto it, and you're still feeding, well, not even at a ceiling, like say 2/3 of the way up the wall. And so you can make a very, very neat situation with the boilers underneath, feeding into the sides, and you've got your zone. So again, the imagination opens up to what you can actually do. Here's a scenario that I want to talk to you more about, because see, we have boiler 1 and it feeds in with the flow going in here. This might be a gas boiler, and say this is a heat pump. But this is a very, very interesting job, and I'll go through it way in a while. But there's one other point about this. If you wanted to put an extra zone and you haven't got a return, there is no reason why you couldn't tee 2 returns together. So you can take advantage of the spare flow and still give yourself 2 boilers and 6 zones, even though now you're using it in a completely different way. You might want to use this for a cold feed or whatever. So and the point here, so you're not stuck with the number of ports in the manifold. But if you were putting together an oil boiler and a heat pump, many people will use different, everyone has their own. You sign your name your way, I sign my name my way. Both of them work for us. We're not stuck with any particular way to do it. So this is a scenario where a guy might decide to put, say, a high temperature boiler in on one side and put a heat pump on the lower connections. And yes, it'll work. But people who know heat pumps will know that there could be conflicts here, because if the gas boiler and the oil boiler run at the same time, you might prevent the heat pump from having full access to the coldest water. I actually don't think you would, but people say that you would, but we've never done it, so I don't know. But in any case, so you could do this, but I want to go on and show you a very, very interesting job. Suppose I have an NRG 4, it costs about 230 euros, something like that. I have a heat pump and I pipe it into the lowest connections with the flow from the heat pump going in the middle left-hand connection. And I take my gas boiler in the middle right-hand connection. And so when both boilers are turned off, nothing happens. If I turn on the heat pump, the flow comes in, goes through the middle chamber, but that has a perfect path up to the top chamber, so you can feed the zones. So here's what's going on. This is not showing temperature. This is showing flow rate. So the darker the color, the more the volume of water passing. So when the flow comes in here from the heat pump, it can't go anywhere else because there's no other connections. This is just a round pipe becoming a square pipe. It comes over to here. There's a suction force here because these zones are calling. It's pulled up here, it comes across down through the zones, the return water comes into the bottom chamber, and the heat pump draws it back. So even though you've taken the flow in the middle chamber, it will work absolutely perfectly to deliver heat out of the top chamber. We go back and we say, now we have the gas boiler, and the gas boiler is taking the return from the middle chamber. The heat pump is turned off, and we're taking the return water up through the boiler, heating it. It goes in through the pipe into the top chamber, turns back on itself, deaerates, feeds the zones. The cold water comes back here and feeds up through this bypass. And now you can see, even though the gas boiler is connected, flow in here, and you're breaking up the water here. Do you see what's happening at all? There's a huge amount of water activity where it's thumping off the inside of the baffle here. It's breaking the air has been released. It comes across down through the zones. The returns come back in here. And so there's the water, and it got maximum, whatever amount of, if 10 litres come through here, 10 litres must go back. So by the nature of water circulating, this will work absolutely perfectly. But here's the trick. We have the heat pump and the gas boiler working at the exact same time. In that situation, the heat pump's only job is catch the coldest water. Just suppose we say, suppose we're pushing to the hilt, we have tremendous delta T, we want the most efficient job you can possibly have. Right, so let's say we have 35-degree water coming back from, they're all underfloor zones or whatever. And you have your water coming back, and it's delivered in, raises it, say 5 or 6 degrees, so it's gone up to 40 degrees. So now the heat pump is delivering across to here, but guess what? The gas boiler pulls it away before it gets up to here. The gas boiler takes 40-degree water, raises it up by 20 degrees, which is tremendous for a gas boiler to have that efficiency. The gas boiler is delivering in our 60 degrees. The 60 degrees is being taken out by the zone. So you've got full, if this zone was say set at 8 kilowatts and this is 3 kilowatts, you have more activity in this circuit than that. If this was 8, you'd have more activity in this circuit. But now the coldest water comes up. It's been pulled back by the heat pump. So now we've got the heat pump working at perfect efficiency. We've got the condensing boiler working at absolutely perfect efficiency, and there's no conflict, and there's no valves, and there's nothing to go wrong, because I'm not speaking just theory, it's pure common sense. If I say to you, I know the flow through on the boiler, I know the flow through on the heat pump, I size my pumps and my flow speeds properly, I know what my zones are doing because I've done my calculations. And at the end of the day, I can actually design a system that before you ever put a screw in the wall, I can tell the person in the house, your efficiencies are going to be through the roof. I would ask anyone to tell me a better way to put two boilers together and keep the efficiencies at that height. So now, so we thought we saw everything, and now we have the strangest thing of all. Just suppose we've got a system working at a low temperature and high temperature, but we want a high temperature cylinder, but we have low temperature here. So what if we took the cylinder from this corner, right? So now when the heat pump delivers across with its say 40-degree water, the gas boiler takes say 25 litres a minute, just suppose, or 20 litres a minute up here, just suppose. You size your pump on your hot water cylinder for 20 litres a minute. Now the gas boiler is taking all of the gas boiler, or the hot water is taking all of the high temperature water, and the heat pump is now, it has to fill the gap, because if there's a vacuum created here because water is being drawn away, something must come back and fix it. The only water available is the heat pump. The heat pump and whatever, and residual water from the gas boiler, because your maths must be right, will feed the zones. So you can have, without mixing valves, you can have a high temperature cylinder heating to full temperature, and you can have a low temperature heating system, and yet you've got no valves. You've got no mixing valves. But because you've sized the system properly, you can actually so have an amazing thing. You can have high temperature and low temperature all happening at the same time. It would be extremely difficult to get that right, but it is very, very possible to do it. And the trick is the sizing of this pump and the coil in the cylinder. Because if the pump and the coil can take the heat from the boiler, there is absolutely no reason why this system wouldn't work with perfectly, and let the heat pump continue with the low temperature and let the high temperature cylinder reach whatever it wants to reach, and at the same time keep our zones working. So it's completely unusual. So I believe after that, if someone said this is just another low loss header, or just another way of putting close couple T's, or it's just another box, I think what we found, and that it certainly isn't. I'm also going to tell you something. I actually don't know the extent of what it does, because plumbers are ringing me up and telling me the things they did, and I'm saying I didn't know you could do that. So as installers are using their imagination, and like I didn't come up with the system, so as installers are putting their ideas together, they're coming back with really good ideas and sharing the knowledge, and that's why the people who use the NRG Zone tend to use it all of the time.
I suppose, lads, we've done multiple systems now at this stage with heat pumps, gas boilers, heat pumps, solid fuel, condensing. I suppose the one that strikes my memory all the time is the one where we did a condensing gas boiler. I think it was a Wolf, if I remember correctly, a Wolf boiler, and a solid fuel. And the one thing I did notice is that the uptake on the condensing of the boiler. Now I know it's a very good boiler, but we got at one stage, I think we got about, I think it's about 800 milliliters within, I'd say within about half an hour of the boiler working. So the condensing was actually quite high on the unit. You know,
and that's with the solid fuel working.
Yes, solid, both were working at the same time. The solid fuel was able to maintain her high return temperature, and the gas boiler was able to maintain a lower temperature coming back, you know. So which obviously it'll all come to temperature at some stages, things will start cutting out. But on the first initial, when you're actually running, before the zones get to the point of where the returns are getting hot, the zones are going to start turning off anyway, because you're going to get the temperature, you know what I mean? So it's fairly straightforward.
Okay. You can see so what's happening inside. The cylinder's taking away the high temperature here, and the heat pump is carrying on its work rate, and so is the gas boiler. So if you decide to use mixing valves, there's utterly no reason why you couldn't put a mixing valve on a given zone and not on the next zone, or vice versa. And you can take you could have a boiler coming from the left and say a zone on the right, or you could have a mixing valve feeding into the manifold, so that you would have high temperature over here, and then you can mix the whole manifold to a certain weather compensated level and still have a lesser mixing valve for, say, underflow heating or whatever. And if your manifold is feeding out to another manifold, again, you can feed it on the way in or on the way out, so it makes no difference whatsoever. Now is an interesting thing where you're using an NG4 to collect two boilers with a high temperature circuit going to heat water, a mixing valve controlling the temperature for all your zones, with, say, underfloor having a lesser temperature, so they have their own mixing valves. So you have full temperature going to your hot water, and at the same time, you have weather compensation on your radiators, and you have temperature control on your underfloor, and it takes very little work. And again, you can see that that kind of work would work out very neatly. Here's a scenario as well where we make a board that actually handles, a standard would handle 4 zones wiring for stats, pumps, clocks, its own fuse, whatever. It would handle 2 boilers. This board costs about 120 euros or something, 120, just over 100 quid. But in any case, you have an auxiliary set of things over here. So for example, yes, it'll handle 4 zones, but if you say wanted hot water priority, there's a way of using the auxiliary relay to turn off whatever zones you want to turn off, or to do, so there are many tricks. If anyone is interested, we can do another session on this board, but it just makes it so easy to wire a system that would otherwise be extremely complex for an extremely reasonable amount of money. Each zone has its own 1 amp fuse, each boiler and a spare control fuse are 3 amp. The main fuse in is 5 amp, and the auxiliary has another 3 amp fuse. So there's LED indication, so any zone is calling turns on an LED. If the mains power is on, the LED lights saying you have mains power. If a boiler is firing, the LED lights here. If the auxiliary function is on, the lights here. So at an absolute glance, you can see precisely what's going on. So this is the Energy Lex, and that's what it actually looks like. It's very clearly identified. There's numbers in each terminal. It's another day's work, but I just thought we'd have a quick glance at it just now. So let's talk about piping methods. We have a boiler here on the left-hand side, either can go, you could take the return temperature from the coldest return water, or you might decide to take it from the middle connection. Say with solid fuel, you might take the return from the middle connection. With a condensing boiler heat pump, it might be best to take it from the bottom connection. You can have a boiler left or right, doesn't matter how many zones. You always put your vent on what I class as the middle connection on top, albeit that it's over at the right-hand side, because that's where the air trap is. Never, ever, if you're going to take a zone off that, which you can do, you must have a vent on it as well. So here's a very interesting thing. If you have a shunt pump on a condensing boiler, the shunt pump will take the hottest water and push it back into the boiler, and now you've lost your condensing, because the shunt pump will put the hottest water directly into return. In this scenario, you use the middle connection as the shunt, so you're pushing the water faster past all the zones, because you might be feeding a lower volume in from your boiler at a given time if there was a bank of boilers, and you're shunting the water around quicker so every zone has equal access, but the shunt water doesn't get at the return water. So for the first time, a shunt pump will not destroy the efficiency of an efficient boiler. You can couple zones together to give yourself a bigger zone. So if I had, say, 1.25 inch zone, I could couple two connections together and come out with one pump and then couple back in. So now I can take much more power here, but remember the old trick, you have to put in as much as you're taking out. But here's a scenario where I have 3 boilers and a large zone taking away, say you have a common zone in an office block or something. Here you are with the same manifold, same money, like 200 odd euros, and you've just done a commercial job. In this scenario, you have, again, 3 boilers, and you can have, say, 2 coupled together and a single zone. So you can have, say, one large zone, a sub-zone for maybe hot water. This could be a weather compensated zone if you put a mixing valve, and 3 boilers that are sequenced or whatever. Again, here's another scenario. You have 3 boilers on one side, the mixing valve. Remember, the chambers matter. So when you're pulling the water down, you can reverse the flow on what would have been, what I class as a flow pipe here, can become a return, because your imagination is going to guide you to say, you're pulling from the bottom chamber, and the second connection, the 4th and the 6th here, connect from the bottom chamber, and they're delivering up through the pipes to the top chamber, and the top chamber can feed the hot water, and the top chamber can feed the mixing valve with the pump circulating. So you're not confined, although the book says flow chamber and says this is the flow, it's completely up to your imagination. So there's a very complex job, again, done very, very simply with weather compensation or, say, underflow heating on the far side here. Again, same scenario, you could have wall-hung boilers, mixing valve separating the temperatures from the high temperature to the low temperature, and again, scenario with your hot water, pressure vessel and cold feed, or the filling system perfectly located on the neutral point. Your expansion is exactly right where it should be feeding the boiler, so everything is good. Here's another, we did this job and I just could not get over the running costs. It was in a hotel, and this is going to take a bit of explaining, but it really, really is very good. So we actually ended up, if I'm not mistaken, we had something like 8 heat pumps. There was 8 heat pumps, and they were being fed from a very large manifold where the cold water was taken down, and a sequencer was bringing in whatever heat pumps were necessary and feeding a primary loop. So the primary loop fed in, went across the chamber, and now we use the middle as a bypass. So we have, all we're doing here is circulating the water past the zones. Any zone can take water, but the water here, the cold water, passes through the heat pumps and it's offered back into the primary loop. Then we take the hottest water from the heat pumps, let's say 45-degree water, and we go down with a pump and we feed a preheating coil in the hotel's hot water system. So we got low temperature preheating on the hot water. Then the water comes back from the coil, it's put through the heat pumps again, and so that can carry on. But the main shunt takes the hot water, the heat pump water, across to this point. At this point, it's taken down into an NRG 4, a little small standard manifold. There's 2 35 kilowatt gas boilers underneath. We're taking the water heated by the heat pump, and in the coldest of weather, our weather compensation manifold turns on the gas boilers. We're taking the same water, we're putting it up to 60 or 70 or 80 degrees, whatever is necessary for weather compensation. And now for the first time, we've got hot water feeding the zones. So the heat pumps are working really, really well for the vast amount of the year without the gas boilers, whenever they want to deliver the heat to the hotel. And at the same time, whenever they want high temperature hot water, the gas boilers kick in, and the gas boilers now feed on the left-hand side of the standard manifold. So the gas boilers are heating the hot water on the exact same system that the heat pumps are feeding the hotel with cold water. Try do that system without those manifolds. That system is in 5 years. We have never had a call back. All I do know is that the running costs are absolutely superb. But it's just a very, very unusual way of going about an extremely efficient system. So again, here's a scenario where we have a shunt pump for a commercial job, big boiler, and we're shunting only the flow water around inside the manifold, through the pipe, through here, down through the gap and back around. So the boiler is able to deliver in, the zones have equal temperature, and then we keep our original boiler. So where you go to a very large premises and you have a monster of a boiler, but you want to add efficiency, you might say put in, say 2 or 3 condensing smaller boilers that add up to maybe the full load here. You don't have to take out the original work. It can stay there so you have belt and braces. But now these boilers can actually be doing the vast amount of work. And if there's really, really cold weather for a week in the year, the old boiler fires. So instead of spending a fortune building a boiler that'll only be pushed to its limit for a few weeks in the year, you let your superbly efficient boilers do 99% of the work. And yes, you rely on the old boiler, but you've just saved the owners of the building a fortune by not having to waste money putting in a boiler they're really going to use. So you can combine the old non-condensing boiler with the new condensing boilers, and both of them will work away perfectly happy. So the energy zone, I believe it reduces the cost of installation, takes down the labor content, takes down the prices of material, it speeds up the whole process. The design process comes down to your own imagination. And remember, we provide a free design service along with the installer. So if you contact us and you have a job to do, you're not stuck with it. We'll give you back a diagram showing the pipework and showing the wiring if necessary. And again, we're quite willing to take responsibility for the system, but put your name on the drawing so that you're providing a superb design service as part of your company, but we're taking responsibility in providing the drawings. If it's a very large job that needs an awful lot of work, there could be a cost. But if it's an ordinary Joe Bloggs the job with basic work, then there's no cost. So there's connection points for temperature sensors. You can look, if you look at this point over here, it's the perfect place for a temperature sensor because it's meeting the flow in both scenarios. And here down here is a perfect place as well for return temperature sensor or whatever. Or if necessary, we can put on a socket any way you want onto the manifold to whatever you want. So it simplifies the design because you now know as much as I know about the unit. If you figure the flow rates and pump sizing and heat loads properly, and you understand the difference between the flow, the bypass, and the return chamber, you decide which is to be the flow chamber, orient the manifold to suit, you can create whatever systems. The most complex jobs become extremely easy. So you have an expansion, a connection for the expansion or cold feed or whatever you want. You can have your expansion connected here, here, here. Connections for the expansion and filling vessels. Sorry, this would be a cold feed. You could take a cold feed in here as well, which is a very good point because it's direct access to the return of the boiler. This is critical. It's completely unobstructed all the way through, and yet the bypass, like with a low loss header, doesn't conflict and dilute the flow temperatures going to the zones. So you've got all of the advantages of a low loss header, except you break away from the fact that you're destroying the efficiency of the appliance by mixing the hot with the cold. You can interconnect manifolds together to make whatever system. We've actually got jobs where you'd have a manifold feeding a manifold, feeding a manifold, and they work away perfectly with it, certainly with complex areas where you'd have a very large boiler house feeding out to sub-buildings, and then the sub-buildings could have manifolds feeding out to, it doesn't matter, because if the pumps can do the job and the heat input is correct, it'll work. When I say dynamic flow and return, the bypass can work either direction. It doesn't matter. Obviously, you don't want to bypass up the wrong direction if the system isn't designed to do that. But for example, where I showed if the heat pump is feeding here, you want it to reverse. So it's dynamic. It can work both directions, depends on how you design the job. You you can have connection points for all these independent zones, so there's no planning out or thinking to do of what you're doing. The box makes common sense as you look at it. And then it isolates the return water in its own chamber, so you can pull it away to be the most advantageous depending on the type of appliance you're using. And then the built-in air separation works extremely well because we're breaking up the volume of water flowing through, and we're letting the volume slow down to a 2.5-inch header here and a 2.5-inch header here. The air rises to the top, you scoop it out. And then you have a uniform temperature with every zone, because no zone contradicts any other zone or in any way influences any other zone. So each zone has equal access to the water if the water coming in is equal to the total amount leaving. And then the units come with inch thick 25mm insulation all around when they're delivered, standard units. So hopefully that was as informative as I can. I don't know how we're going time-wise. I don't know how you're going about it. But Jens, are you in a position to open up the microphones if anyone has any questions?
I think they can unmute themselves or just write in the chat.
Hello.
Yeah.
So I think I have to put my hands up and say I didn't have the right head on for this tonight. I've completely underestimated this thing. So I'm just hoping that it's recorded somewhere so I can.
It is recorded, yes.
Right. It sounds quite an amazing and very flexible piece of kit. What's the target velocity inside the box itself? I was just looking at the air separation and how you go for turbulent flow.
What is I missed the first word.
So what's the target velocity? I mean, the target velocity of your system, somewhere around 1 meter a second.
The minimum is 0.6 of a meter. Jens would be the one to answer that question, but we're well and truly inside for that site, for inch connections.
Yeah,
we're well and truly inside when we make bigger manifolds. So to have 0.6 of a meter for inch pipe, even for 2-inch pipes feeding left and right, I think you need 1.5-inch pipe. We're at 2.5 inch. 2.5 inches is like 4 times the size of 1.5 or 3 times. So we've really gone over the top. People say the manifold is big. We did it for logical reasons. It costs us more to make it bigger. There's more welding, there's more metal. You know, there's hassle trying to convince people to go the extra bit and find the room. But the idea is that when you put it in, the air is just literally gone. The air passes once and it's gone. So we're damaging our market by making it so big, but we're improving the work. And I think that's a good bargain. Do you know what I mean?
Okay. Do I take it Ireland is imperial then? You talk about 2-inch pipe and the like.
No, the reason I'm saying that is I would have the impression that a lot of people would say, we'd always work in metric, 28 mil and 22 mil and whatever.
Yeah.
But I find that a lot of people still refer to.
Okay. Oh, okay.
So, and it would be 70 or 72 for the size of the chamber inside, and 42 being the size for the, would be acceptable. So 42 pi r squared to 72 pi r squared, it's humongous. Do you know what I mean?
Yeah. I get it. Very, very, very interesting, mate. Very interesting.
Yeah. There's a lot more than meets the eye, isn't there?
Yeah.
And you see, when people don't understand it and they're criticizing it without actually trying it, it's frustrating. But at the same time, it's part of the game, isn't it?
Yeah.
Yeah. So do you think maybe I went too fast in that it was a lot to take in?
To be honest, it knocked me off my feet. It wasn't anything like I thought it was going to be. I was sitting down here for a bit of a relaxing hour, whereas really, I really needed to get my head tuned into it and focusing on it. Because once I realised,
you get the exam paper and you'll see how
once I realised it was more than I thought I was already on the back foot.
I know.
But I should definitely be watching the video again for sure.
Yeah.
Very good.
As I wish I had full knowledge of all the different configurations, but there are so many people coming up with innovative ideas. It's absolutely fabulous. I'll give you an example. Did I mention that you can fit it up sideways? It changes the game. It really is interesting. You can actually use it sideways and it takes up by far less room. You have an open vent system that par excellence. You still carry on with your zones. You can take a condensing boiler from the bottom. But if I was to go into all of the different things, like I'll give you another example, where we had to do a design where people wanted air conditioning, water-based air conditioning, and they wanted heating from the same convectors, fan-assisted convectors. So we put in a manifold onto chillers, we put a manifold onto heating, and we teed the outlets together with non-return valves. And if depending on what way the valve is, the two manifolds can either be heating or cooling at the same time. So do you see what I mean? It's limitless to what you can actually do. So I love it, to be honest with you. I get a great kick because guys come in and they say, look, I have a real awkward thing here. Can you solve it? That's the challenge we love. Give us something that we haven't done before, because it's just really, really interesting.
I suppose, Harry, it hasn't, we haven't even covered the solid fuel side of it, right? You know what I mean?
We haven't. The solid fuel is really, really interesting, isn't it? But I don't suppose that would be interesting for guys maybe in the southern part of England, whatever, but in Scotland and certainly in Ireland, it's extremely interesting, but it's extremely versatile because remember, one of the attributes is you can have a gravity system with no pump on one side, and you can have a fully pumped system on the other side, and they don't conflict. The solid fuel will drift heat in at its pace, and the high velocity system will come in at the other side, and yet there's absolutely no conflict. So you can have high pressure, low pressure, which you got to volume I'm talking, or velocity. You can have high temperature, low temperature, and basically you can really combine. You can let your imagination really rip.
I just linked the manual in the chat if anyone wants to read.
All right, if you download the manual,
take their time and read about it.
Yeah, I saw that. Yeah.
And then one last thing I want to say to you is the NRG Lex is every bit as interesting as the manifold, the wiring center, because again, the tricks you can do with that, and it's such an economical product for like just over 100 quid. You're doing your own wiring. You can put in any kind of control onto the thing. You can use it for multiple boilers, even more than 2 boilers if you had to, because you can use the auxiliary to bring in another 2 boilers. So you could have, 4 zones and 4 boilers from a unit that costs like 120 quid. Could I suggest that if you ever wanted to, again, if you contact me and you want to have a rerun, well, obviously I'll put the video, but if there are any questions, you can contact me at info@NRG awareness, the 3 letters, not energy.com. So if you have any systems that, or even if you have an idea in your head that you want to just think about and you want to draw it up, why not? It's all to do with learning. Actually, if you look at what's behind my back there, that was our test scenario. There's the solid fuel fitting in on one side, and that's a sealed system, open system on this side, a gas boiler working at, it was delivering, if I'm not mistaken, 70 degrees, was it, Rich?
Yeah, 70.
65 to 70. The heat pump was going in at, putting in at 45. The gas boiler was putting it up to about 60. And then the solid fuel was taking it and putting it up to 70, and the solid fuel was, so we were actually delivering 70 and taking back about 35, and everything was working hand in hand. So it just made life so simple. What we were doing there was testing, could we use it on open systems with sealed systems, high temperature with low temperature, and literally, I suppose we learned so much at that time that it just gives great enthusiasm to think that it's a really effective product. And there's one other thing I'll say to you, and I know I say it ad nauseum, but we have never had a system that didn't work. And it's common sense. It's a plumber's solution. It's common sense. Hot water rises, cold water falls. If the velocity is carrying enough volume to deliver to the zones, and the zones are taking away that water, and the delta T is right, the system is going to heat. So your efficiencies are up, your delivery rate is up, the customer bills have to go down. So that's why we're getting such incredible customer reports back about extremely good running costs.
Harry, a couple of lads are asking as well, could they have the link for the video when you're finished, obviously?
Yeah, if I can figure out how to get it. Yeah. Is there any other particular question I can help anyone with?
No, that's good. It'd be nice to see, the NRG Lex. Like you say, you'd probably do another evening or something. That'd be good.
No problem. I can, if you have particular questions that you want to address, I have no problem doing that. But as I say to you, really what I would love to move on to is the control side and how it matches with the heating side, because that really releases your imagination. And if you consider that with a blindfold on, you can actually fault find the system because you're touching exactly what's going on everywhere. And if you have the 7 LEDs telling you what zone is calling, what boiler is on, what auxiliary function is happening. So even within seconds of going to any size job, you know what's going on. Remember this, if you can follow the theory for the NRG 4, which is the size of, not the size of a cornflakes box, but not far off it, you can design a hotel because there's nothing changes. Whatever theory happens in the smaller unit happens in the big unit. But for some reason that I can't tell you why, the bigger units work even better. So it must be to do with more volume or something, but the commercial jobs you have just absolutely sing.
Harry, one of the lads are asking about dirt separator.
Yeah, we have a design to build in a dirt separator into the unit. But again, the criticism we constantly get because people don't understand the system is that they say we're too expensive. And they say, so if we built in a dirt separator, nobody would say, they'd say, you can't have it. If you understand me. So we're held back because people won't try it. But if our market was right, the design is finished. We can build in a dirt separator. It's not a hassle, but just now it's not viable because too many people are saying it's too expensive. Can I ask you a reasonable question? Can you tell me if that little manifold, the NRG 4, can handle, say, 3 zones and 2 boilers, or one, I think it can handle 5 zones and 1 boiler. It gets rid of the air, it separates out all of the thinking, you have very, very good condensation. That unit costs about, let's say, 220 quid. Could anyone tell me they think it's too expensive? There's not a hope in hell. You couldn't make, the amount of welding inside in that unit is unbelievable. There is nothing like it on the market. If I just have a shell, like a low loss header, I have the outside, I do some welds around a bit of pipe and I sell it for 500 quid or 400 quid. This thing is like taking 10 times longer to manufacture than a low loss header. So it's not expensive. It's actually way underpriced if the truth be told.
Is it UK manufactured?
We work with a guy from Eastern Europe.
Where is your partner based in Eastern Europe?
I always get it mixed up. Is it Czech?
It's in Croatia, on the border to Italy.
Croatia.
Yeah. And he's an incredible electronics genius guy. So we have a building management system, or sorry, a telephone operated temperature control system. I have it in my own house. So you have an app on your phone and it can control like of an energy lex, but you see the temperature in your rooms, and it also tells you the quality of the air in the room. So it will turn on your heat recovery system, the same app, same thing on your phone. It will actually, we also make air disinfectant systems for where you have bacteria and virus in the air. It'll control that as well. So if you have it in a commercial place, like if you have in a doctor's surgery or in a waiting room, or maybe a solicitor's waiting room or a chemist or something, they're controlling the heat, they're controlling the air quality, they're changing the air, and they're monitoring the quality of the air with regard to viral infections and whatever. All these things are on our site. What we have is very interesting. We're just about to introduce it into the US, and it is absolutely class. So we've got 4-inch centers so it makes it much easier, whatever, but it's a much bigger unit. And we also have all the valves and pumps and whatever built in. If you look at our website, we supply with the manifold, if you want, the pumps, the isolation valves, but the isolation valves have built-in non-return valves, all the vents, whatever, and we do a special offer then if you get the kit. So if you buy a manifold and the pumps and the isolation valves with the non-return valves, there's a reduction of like, what's the reduction, Jens?
15% discount.
15% discount. So it makes it extremely viable.
I suppose, Harry, go back to the wiring side of it. No, I suppose I am a bit biased. I'm using these a good amount of years now at this stage. I can wire a 3-zone system in less than an hour, and I'm taking my time. So it's quite
and that
fast.
would be boilers and all the controls, everything.
Yeah, everything. So it's quite handy.
Useful for radio controls because there's a connection for everything, and the switching isn't done by your wiring. The switching is done by the board, so the complications are eliminated.
Yeah. And actually, as the more wireless stuff is coming out, the time is going down because you're not having to wire up as much. You know what I mean? So it's just getting faster and faster.
So lads, could I ask you a favor? there's a lot of people are criticizing the cost, and a lot of people criticizing what they think it does. Would you be kind enough to put a comment on whatever Facebook page you're on to let people know that at least it's worth looking at? I'd be very grateful, because because as I say, it's unfair that people are looking from afar and not actually trying it and still criticizing it, when because there's so much effort put into it, if you understand me.
I suppose the one, besides designing the units and what have you, Harry, the one thing that I tend to find is when I go to individual properties, what have you, and there's a lot of undersized pipework. Obviously we'll have a look, and we obviously can't see into the ground and what have you for so much of it. We have come across a couple of occasions where there's been a lot of half-inch used or whatever the case may be, and we ended up putting them on these units and separating all the zones out, what have you, and it actually got it over the hump, and all of a sudden radiators started to work. Do you know what I mean? So
You remember the criticism we got about the smell where the paint was burning on the rads for the first time, because the rads were heating properly for the first time.
yeah, exactly.
Yeah. Okay, lads. So unless you have more questions, we'll leave it at that. But I'm very delighted that you turned up, and I'd love to think that we could do some more whenever you want.
Yeah, thank you.
Okay, thank
Cheers,
you.
Harry.
Appreciate it. Thanks so much.
Thank you, guys. Thank you.
Bye.
Bye-bye.
Thank you very much.
Okay, thank you. No, bye.
Thanks, Harry.
All right, thanks.